welcome to this week's Cron seminar. We have two talks this week. Our first speaker is Fateme Hafezi from the Institute for Advanced Studies in Basic Sciences in Iran. She is interested in implementing machine learning algorithms in various fields from a physicist perspective. During her master program, she applied machine learning to the field of soft matters and astrophysics. So welcome, Fateme, and you may want to start the presentation.
Thank you for introducing me. And I was saying thanks, Professor George Karniadakis, to give me this opportunity to talk here. And it's my honor to be here to listen to your comments or answer any of your questions. Please feel free if you have any question to interrupt me and ask your question. And if you have any other questions or comments, you can send me an email in this address or send an email to my supervisor, Dr. Nedai, in this email. Let me enter. If I want to introduce my supervisor, I should say he's a associate professor in soft matter physics and at our Institute for Advanced Studies in Basic Sciences. And he's also a head of a research center for basic sciences and modern technologies. Okay. First of all, I want to speak a little about the introduction of our works, and then go to motivation, and then speak about the methods and results. Due to the fact that the audience here are from different fields, I want to speak about the introduction of the physics that we used in our this article. As we mentioned in the title of our works, we want to calculate the potential of charged particles that are surrounded by conductive walls. This problem is very important in computational electromagnetic simulation, molecular dynamic simulation, or chemistry, or even industry. For example, a capacitor in industry is very useful, and in the capacitor, as you can see, we have many charged particles between conductive plates that it is very important for us to calculate the potential of them, and then calculate the amount of energy that capacitor can save. But the problem is that conventional capacitor just can save low amount of energy in order of 1 microfarad to 1000 microfarad. And but we have supercapacitors that has porous plates, conductive plates, and with these porous conductive plates, we can have more charged particles between these plates, and whenever we have more charged particles, we have more potential, and we can have more energy storage. For example, look at these two pictures. Pictures one show capacitors, and I don't know, not sure you can see it, but I can read it for you. For example, this capacitor, the capacity of this capacitor is in order of 22 microfarad, and this capacitor is about 4,700 microfarad. While this is a supercapacitor, picture 2, that the capacity of this supercapacitor is 100 farad, and there is a difference between them. In some cases, we have to change the battery. We have to choose supercapacitors instead of batteries. Okay. Now the problem is that how we can calculate the potential of these charged particles. It has an easy answer. We can calculate. We can evaluate the potential by solving this equation, Poisson equation. And here phi is the potential and rho is the density function, charge density function. And in our case, here rho is discretized, and we can show it by this. And here epsilon 0 is a vacuum permittivity, and it is constant here. Okay, but the problem is when we have a charged particle near the plate, conductive plate. This conductive plate acts exactly like a mirror. So we have the amount of charge exactly on the opposite side of our plate with opposite sign. And we can calculate the potential with summation of the potential of these two particles. First terms is the potential of our charged particle, and the second terms is the potential of image charged particles. This method that I described it called image charged method. But consider if we have lots of charged particles between two parallel conductive walls. What will happen? Because we have two parallel conductive walls, it is exactly like two parallel mirror, and so we have infinite series of charged particles. So we have to have infinite terms in this sentence. Okay, but when this problem with this symmetry turns to supercapacitor, supercapacitor, that it is a asymmetry, we could not solve it but by image charged particle, image charge method. So we have to use analytical method. There are some packages or methods that could solve these kind of problems, but now I want to speak about Javier package. Javier package is is presented by Professor Nedai, Professor Qasemi, and Biagui et al. And it is a simulation package, molecular dynamic simulation package that it is very useful for this kind of problem. They can use easily with PLT algorithm that I will introduce it in the next slide. They transpose Poisson equation with discrete density function to Laplace equation with modified boundary conditions, and then with finite element method they they simulate any kind of super capacitor. So what was the problem? What was our problem that motivate us to present another method, another model? The problem is that in every snapshot, we have to use a finite element method. So during the simulation, we have to maybe we have to have increase in the number of charged particles or decrease, and in every time step, the charged particles could move, and so it was very time consuming. Apart from Javier package that, as I said, presented in 2020, we familiarized with the work of the research of Racy et al. And in 2019, which they present a physics informed neural network that are neural network that obey physical laws. So these two kind of research motivate us to present this model. Okay. First of all, I want to speak about the method, the PLT algorithm, especially the PLT algorithm that we use. And then I speak about the model. But up to this section, if you have any question, please feel free to ask me.
Fateme, is Caviar is Caviar a free code open source?
Yeah, it's free code, and after them I can put the link of this code in the chat
Okay.
box.
Yeah, thank you.
Thank you. Okay. This is the flow chart of our method. We first of all use a PLT algorithm and creating the reference data set. And then we split our reference data set into trained and test set. Then train our models which have random forest, neural network, and pin-based model on the train set, and then test in this model with test data set and as well as hyperparameter tuning, and then choose the best model. Okay, what is the PLT algorithm? As I said earlier, in our work, whenever we want to calculate the potential of the charged particle, we have to calculate this Poisson equation. But due to the PLT algorithm, we can split the potential into two parts: singular potential and smooth potential. Look at this picture, picture A. In our problem, in this case, we use a spherical container, spherical mental container, and we put some charged particles inside it. Due to PLT algorithm, this part, singular part, is calculated by this equation, and it can easily calculated by this equation. And the potential of the smooth part is calculated by Laplacian equation with modified boundary condition. How could we calculate this modified boundary condition? If you minus singular potential from both sides of this equation, and then calculate each part of this equation in the boundary, we can calculate this. So the smooth potential in our boundary is the potential of these charged particles in our boundary plus potential of the total potential that are presented in the boundary. And then in our model, we use only 26 points of this boundary condition in our model as an input. And now we present a model that predicts the smooth potential, which is could be calculated by Laplacian equation. So the physics law in our work is Laplacian equation, and the modified boundary conditions. Okay, apart from those 26 modified boundary potential on our boundary, we have the position of the place that we want to predict the potential on it. So our input is x, y, z plus 26 potential on our boundary, and our output is a smooth potential on the position of x, y, z. And we can, after we predict the smooth potential, we can easily summating the predicted smooth potential with this term, the singular potential, and then calculate the total potential. Okay, apart from the our input layer that consists of 29 features, it is very important to know what is our loss function. Our loss function consists of 4 main parts. The last part, the last term, is just a term that prevents the model to overfit, and so I want to speak about the 3 terms. Our loss function equals the mean square error of our data. The first term is mean square error of our data that in the conventional neural network is presented. So here U is the predicted potential, smooth potential, and phi is the true potential. The second part, MSEF, mean square F, what we means is that our mean square error of our function, that is Laplacian equation, And the third part is the boundary condition, that is the predicted potential in 26 point on the boundary. And that's it. What I mean about these terms is that if we put 26 position of the put 26 position of the points that in our boundary, we have to have the smooth boundary potential as an output. So on the other hand, we have the boundary potential as our input. So we can calculate it by this equation. Something else that I have to say here is lambda 1, lambda 2, lambda 3, and lambda 4. We set lambda 4 as 0.001, and it was not our hyperparameter. But we set lambda 2 and lambda 3 as our hyperparameter, and lambda 1 is equals to 1 minus the summation of these lambda. So the summation of all of our lambda is equals to 1. Then generally the hyperparameters of our model consist of lambda 2, lambda 3, and the number of neurons and the number of layers, hidden layers. Okay, this is a schematic of our proposed model. As I said earlier, our input layer consists of 29 features. Our output is a smooth potential, and then we implement these terms, and with summation of these terms, we calculate the loss function. Okay. If you have any question up until this section, you can ask me. If not, I can continue. Okay. Let me speak about the results. First of all, our main purpose was present a pin-based model, but to compare our results with other methods, we compare our pin-based model with random forest and neural network. We choose random forest because it is very fast learner method, and time is very important for us. And we choose neural network to show that if we implement this physics law in the neural network, what will happen. Okay, please take a look at these figures. They are the results of our train set, and the vertical axis here is true potential, and horizontal axis here are our predicted potential. Here the right one is the results of pin-based model, and in the middle picture is the potential of the predicted potential of neural network, and the left one is the predicted potential of random forest. As you can see, neural network was not trained well at all. And I think this is because our data are imbalanced and it couldn't work well. Because in higher potential, we have lower number of data compared to the low potential. And random forest wasn't too bad, but if you see precisely, you can see the random forest could not predict the higher potential. But the pin-based model, our proposed model, worked well in the trained data set. But we evaluate our model, we test our model and test data, and since neural network did not work well, we do not compare the neural network, the results of neural network on test set. So we compare pin and random forest on the test set. As you can see in random forest, again, the potential of higher the predicted potential of higher potential was not good at all, although pin-based model worked well. But in our case, it wasn't enough to test our model just with our test set. So we implement extrapolation data set, which have the modified boundary conditions that are not even in test set or train set. As you can see again, pin-based models worked better than random forest model. Okay, up until here, up until these steps, we predict the potential of just one charged particle in a spherical container. But in our our purpose is calculating the potential of many charged particles. Hopefully, because the Laplacian equation is the linear equation, we can calculate the potential of, for example, 10 particles by predicting the potential of each particle separately, and then by summating this smooth potential, we can calculate the total potential. Look at this figure. The vertical axis is mean square error, and the horizontal axis is the number of charged particles. As you can see, the mean square error is not dependent on the number of our charged particles. So we can say that we can easily calculate the many charged potential, the many charged particles separately, and then summating them with each other. Okay, what was this conclusion? I summarized the conclusion into three main parts. First one is that we found out our pin-based model trained better than random forest and neural network. Random forest actually, although it was a fast learner, but it could not predict the higher potential. And while neural network could not be true. Second part is our pin-based model predict the potential on the test set with mean square error of 0.06 and R2 score of 0.90. And the results on the extrapolation set is mean square error of 0.089 and R2 score of 0.85. That is good enough for us. And the third one is that we can predict the potential of more than one charged particles by summating each charged each potential separately. Okay. Now I can, if I have any question, I can answer it. My talk is finished.
Hi, this is Adar from Brown. I have a short question. Can you please explain a little bit how you did the random forest and a bit about the hyperparameters you chose? Like what's the depth, how many samples per trees? Because you claim generalization, just this is tightly coupled with the parameters. So can you please elaborate on that?
Okay, your question is that how random forest trained in this train set? Yeah.
Yeah, what parameters did you choose for the random forest?
Yeah. The random forest, the input of the random forest is exactly the input of our pin-based model, and the output was that. And for hyperparameter tuning, we only have the n underline estimator as our hyperparameter. It was just this hyperparameter. And if I'm not mistaken, the hyperparameter that we choose, what I mean is that the number of trees was 100, if I'm not mistaken. Yeah.
And how,
am I
like
answering the question?
Yeah, do you remember if you used something like the depth or the samples per leaf, things like that?
Oh, no. I don't use it. I use anything.
So, and you use
sorry, could you open up your video, your camera? I mean,
sure, yeah, I can do that.
I'm sorry. Sorry to interrupt.
Yeah, no worries. Can you see me now? Hi.
Yeah. Good.
Cool. Right. So yeah, I was asking mainly because, okay, did you use like a sci-fi or something standard like this to implement the random forest?
No, just we implement random forest as I said. I mean,
Yeah, but you used a package. Probably you did not implement.
Yeah. We use scikit-learn.
Right. So I don't remember the actual default values, but if you want to do some generalization and get more from your distributions, then I'd suggest if you can tune the depth and the number of samples per leaf, then you'll get more generalization. You can enlarge the number of trees and play with that to kind of satisfy what you need. And you might be able to extract more from the random forest if you play with the parameters. That's the main question I had. But yeah.
Okay.
All right.
Thank you.
Thank you. Awesome. Thanks.
Yeah, I actually have a question. Could you explain why did you choose random forest as comparison? Because random forest, decision tree, they're originally designed for classification problems, but now they can be applied to regression problems as well. But I want to know why did you choose this as a comparison?
First of all, we use random forest regression, and so with random forest regression, we can do some this kind of regression problems. And the second is that we just want to have a method that we compare our results to them. So we use random forest, and the main reason is that it learn fast, and just because of this, and we choose random forest. And another thing was random forest totally is prevent overfitting. Yeah, but if you have any other suggestion for machine learning algorithm like random forest, I mean that was not neural network, I will be happy to.
No,
hear
I'm
it.
just curious. Why did you choose this? Yeah, thank you.
Okay.
Uh,
Do we have any question? George, do you have a comment?
Hi, Fateme. So I was wondering if you want to extend this work. So I don't know what your plans, but you could use DeepONet to generalize this to different domains, different configurations, and so on. And in fact, the talk next will present a new paper by the UPenn group on how to extrapolate. So what you're using pins, and it's good work, but as you run different configurations, you can actually accumulate that knowledge into a DeepONet, and you can do physics-informed DeepONet. So then you can actually generalize, and you will see, if you stay online, you will see the next speaker how he introduces 4 or 5 different methods to extrapolate. So to both geometries and different parameters, larger potentials, and so on. So I also wanted to welcome. I think your advisor is online, right? So I wanted to say hi to your advisor, Hassan.
Yeah, he's here too.
Hi, George. Yeah. Hi, Jordan. Thank you for your time and letting Fateme to explain the works. This is a good opportunity for her and for us. Thank you.
Yes, of course. You're welcome. We have other Hassans in our group, so I'm very familiar with the name. But
Yeah.
Fateme did, I saw the paper and I invited her, and I thought Fateme did a very good job. Excellent.
Thank you. Thank you for your comments also.
All right. If there's no more question for our speaker, thank you for your wonderful presentation. We will move to the next talk, so you may want to stop sharing.
Yeah.
And our second speaker is Ming Zhu, who is currently a PhD student in Dr. Professor Lulu's group at the University of Pennsylvania. He obtained his bachelor degree in chemical engineering at Tsinghua University. His research focuses on improvement of the physics-informed neural networks and deep operator networks, as well as their applications in geophysics and chemical engineering. So welcome, Ming. So you may, I see your screen. You may want to start.
Hi everyone. Could you see my screen?
Yes.
Thank you. Today my topic is about the reliable extrapolation of deep neural operator informed by physics or sparse observations. And here are the author.
Min, can you go closer to the? We cannot hear you very clearly. Maybe you can go closer.
Oh, okay. Sorry. Can you see my?
Now, yeah.
This? Okay. First, let me briefly introduce the architecture of DeepONet in case that someone are not very familiar with it. A DeepONet has 2 sub-networks. One is the trunk net and another is the branch net. The trunk net neural networks are usually limited to solving the interpolation problems, and it would fail if the new input is outside the support of the training data set. In real applications, there is no guarantee that the inference stage is always in the interpolation range, and the extrapolation would lead to a very large errors. Figure A shows illustrative examples where we trained two fully connected neural networks to learn the simple function that is y equal to sine 2 pi x. The two neural networks perform very well in the interpolation errors. However, those two networks have very large prediction errors in the extrapolation ranges. Also, the difficulty of extrapolation has also been observed in DeepONet. When we aim to use DeepONet to learn an operator, we usually generate the training data set from a Gaussian random field with predefined kernels. A typical choice of the kernel is the RBF kernels that is in these expressions, where the L is correlation length. This is very important parameters that in our work. The value of L determines the smoothness of sampled functions, and a larger L leads to a smoother functions, like the L equal to 1. Several functions randomly sampled from space of GRF with different L are shown in the figure B. Here, if the correlation length for training is different from the correlation length for testing, then it is extrapolation. The error of extrapolation can be represented by the difference between the L train and L test. Here, let me use two examples to show the two scenarios of extrapolations. One example is the antiderivative equations, and another example is the diffusion reaction equations. For both problems, we choose L train and L test in the range from 0.1 to 1.0. The training data set are chosen is chosen as 1000, and the error of the DeepONet trained and test data set with different L train and L test are shown in these two figures. As we can see, that when L train is equal to the L test, which is the dashed line in these two figures. It is the interpolations, and the error is smaller smaller than 10 to -2. In the bottom right range, where the L chain is larger than L test, the error of extrapolation is larger. When the L chain is smaller than L test, which is the left top range. Although it is still extrapolation, the DeepONet can achieve small errors. This because DeepONet can predict accurately for smooth functions. And here's the extrapolation for functions with a smaller L is denoted by the EX plus, whereas the extrapolation for functions with larger L is denoted by EX plus. So far, so good. Any question? Okay. And to qualify the extrapolation complexity, we measure the distance between two GRF using the W2 metric, which is the distance function defined between probability distribution on a given metric space. Intuitively, if each distribution is viewed as a unit amount of the Earth's point on n, the matrix is the minimum cost turning one pile into another, which is assumed to be the amount of the Earth that needs to be moved times the mean distance it has to be moved. The relationship between the arrow and the W2 distance is shown in the figure D and figure E for the antiderivative equations and the diffusion reaction equations. The extrapolation arrow grows with respect to the W2 distance between the two GIF space. Therefore, the W2 distance between the training and the testing space can be used as the matrix of the extrapolation complexity. To further understand the extrapolation arrow, we use the diffusion reaction as examples and investigate several factors that contribute to the extrapolation arrow. The correlation length of the training dataset is 0.5, and the bottom of the U shape is achieved at the transition point. To achieve to the left of the transition point, the model is underfitting, and to the right it is overfitting. There are several factors that affect the model capacity, such as the network size, that is the figure B, and the training iterations, that is the figure C. Here we show that the test arrow extrapolation plus also has a U shape compared to the interpolation. The extrapolation plus has a larger arrow and earlier transition point. Also, it is well known that a larger data set leads to a better accuracy for interpolations, as shown in figure D. For extrapolations plus or extrapolation minus, a larger training data set still leads to smaller test errors. However, the improvements exhibit a diminished trend as the training data set goes very large. And another factor is the activation function. For branch net, we use value in all cases, and for trunk nets, we consider 4 activation function widely used in deep learning, including the hyperbolic tangent, the ReLU, and the sigmoid linear units, and Gaussian arrow linear units, or GLU in abbreviate. In addition, we explore the HET activation functions defined in these equations, and this function just look at HET. The correlation lengths for training and testing are 0.5 and 0.3. In the figure E, the ReLU and the HET have similar results and outperform the rest of the activation functions. The GLU also presents satisfactory performance despite the overfitting after a certain number of iterations. Besides the commonly used activation functions, we also consider the layer-wise locally adaptive activation functions, that is called the LAAF, in the form of sigma n times A times X, where sigma is a standard activation function above, and n is a scaling factor, and A is a trainable parameters in each layer. The LLAAF introduce a the tunable parameter in each layer, thus leading to a local adaptive activation function. With the other setting remaining the same, LLAF with the optimal and slightly outperforms the non-adaptive activation functions in figure E. And LLAF hat and LLAF ReLU performs the best among the 5 activation functions. And most importantly, the tendency of overfitting is alleviated significantly. Next, in general, it is very difficult to have accurate prediction for extrapolation. Hence, in order to reduce the extrapolation error, it is essential to have additional information. Here we consider the following 2 scenarios and develop corresponding methods to address the scenario problem. One is the physics, which is the governing equations of the systems with suitable initial and boundary conditions. And another is the sparse observations, which means that we have sparse observations of the output functions at n locations. Since we aim to handle any input functions, the first step is to determine whether V is in the range of the interpolation or extrapolation. If it is interpolations, then interpolations or extrapolation minus, then this problem becomes very trivial because we only need to predict the output by the trained DeepONet. Otherwise, it needs to extrapolation via the proposal methods. On the one hand, if we know the physics, we could calculate the W2 distance or the mismatch error of the physics, and if it is larger than the threshold, we could use the fine-tune with physics method. I will introduce this later. And if we have new observations, we could also calculate the W2 distance or the mismatch error of the observations. Then, if it is larger than the threshold, it is also the case of the extrapolation plus. We could use the fine-tune with the new observation method or the multi-fidelity learning method. And important question is that how could we decide the threshold? We could learn it from these figures. We denote the first the mismatch error of the physics is defined by these equations, where the omega is the domain of the PDEs and the mismatch error of the observation is defined use the root relative square error. The form is very similar to the L2 relative error, but since the point is very sparse, it is not exactly equal to the L2 relative errors. And we denote the value of the epsilon physics or epsilon observation for L equal to L trim by the epsilon zeros. And in the interpolation and extrapolation minus ranges, the value of the epsilon physics or epsilon observation is close to the epsilon zeros. So we can see it in the figure A. In the extrapolation plus range, the value of epsilon physics or epsilon observation is much larger than the epsilon zero. Moreover, for the two space with larger W2 distance, the mismatch errors are also larger. Therefore, we can select the threshold as alpha times the threshold 0, where the alpha is larger than 1 is a user specified tolerance factors. And then compare the epsilon physics or epsilon observations with epsilon. If it is larger than epsilon, then it is extrapolation plus. Otherwise, it is interpolations or interpolation minus. We first discussed about how to extrapolate with additional information of physics in the algorithm 1. First, fix the input of the branch net to be the given input function v. And then sample the two data set of the training points of TF and TB for the equation and the initial or boundary conditions, and choose the weight of the WF and WB. And finally, train all the parameters of or a subset of the parameters of the network by minimize the loss function, which is the combination of the PD residual loss and the initial and or boundary condition loss. As the branch net input is fixed as the V, this fine-tune method works in the same way as pins. Compared with pin, with random initializations, a pre-trained DeepONet provide a better initializations, which makes the training much faster, especially when the interpolation complexity is small. And also that's why the fine-tune with physics method can achieve a better accuracy than the vanilla pin. DeepONet, since DeepONet has two subnetworks, a branch net and a chunk net, and thus we could choose to fine-tune the entire DeepONet or just one networks, while other parts of the network remain unchanged. Moreover, as each subnetwork has multiple layers, we can also only fine-tune certain layers of the subnet. In these studies, we consider 4 approaches: the fine-tuning both chunk and the branch nets, fine-tuning the branch net only, fine-tuning the chunk net only, and fine-tuning the last layer of the chunk net only. The next is about the extrapolation. We are fine-tuning with sparse new observations. The first is called the fine-tuning with new observation alone, or abbreviated as FT observe A. As the pre-trained DeepONet is not consistent with the ground truth of the observation, we could fine-tune the DeepONet to better fit the observation. Specifically, we further train the DeepONet by minimize the mean square error of the new observations alone. The approach is simple and has low computational cost. However, as the new observation number is usually very small, it may have the issue of overfitting and catastrophe forgettings. Considering that the factor that both the training dataset and the new observation satisfies the same operator, they can be learned by the same DeepONet at the same time. Hence, we propose the following fine-tune approach to prevent the overfitting. That is called the fine-tune with training data set and new observations together. Instead of fitting the DeepONet with only the new observations, we fine-tune the pre-trained DeepONet with new observed data together with the original training data set T. We are the combined loss LT time plus the lambda time the loss observations, where the loss T is the original loss for the DeepONet, and lambda is a weight. Compared with fine-tune observed alone above the fine-tune of the observation we together keeps learning from the DeepONet training data set. We are the loss of the LTs, which mitigates the problems of the catastrophe forgettings. Moreover, the LTs has an effect of regularizations to prevent overfittings of the new observations. By tuning the value of lambda, so we can balance remembering original informations and learning from the new informations. And the algorithm, this looks pretty simple. That is, first fix the input of the branch net of the to be V, and then fine-tune the net by minimizing the loss of the observations alone, or the loss of the DeepONet training dataset combined with the loss of the observations together. In the all previous method, we use the idea of fine-tuning. Here, we propose different approaches based on multi-fidelity learning. The idea of multi-fidelity learning is that instead of learning from a large data set of high accuracy, that is the high fidelity, we only use a small high fidelity data set and combine with another data set of low accuracy, that is low fidelity. Specifically, as sparse new observations, D is the high fidelity data set, while the prediction from the pre-trained DeepONet is a low fidelity data set. And we integrate high and low fidelity data set. We are two multi-fidelity methods that are multi-fidelity Gaussian process regressions, or MF-GPR, or multi-fidelity neural networks, MFNN. In MF-GPR, we model the high and low fidelity functions by a Gaussian process with RBF kernels. Then the model is training by minimizing the navigate log marginal likelihood on a data set. In MFNN, we have one for connected networks to learn the low fidelity data set, and another for connected neural network to learn the correlation between the low and high fidelity. And also the algorithm is the first to compute the prediction of the input function, and then samples a set of dense points and as the low fidelity data set, and then use the new observations as the high fidelity data set, then train the multi-fidelity model on the multi-fidelity data set. So that's all about the method. Any questions so far? Okay. Then let me introduce three experiments to show how we use those methods. In this section, we test the proposed extrapolation method with different PDEs for all the experiments. The Python library DeepONet is utilized to implement the algorithms and train the neural networks. We demonstrate the effectiveness of explanation methods. We consider three different baselines. One is the pre-trained DeepONet, and another is the physics-informed DeepONet, and the last is the Gaussian process regression that is called the GPR. In GPR method, we only use the new observations instead rather than using both high and low fidelity data set. First example is the advection equations. Here is the equations, and with the initial conditions sin pi x and the boundary conditions sin pi t over 2 to make sure that the parameter vx is larger than 0. So we take it in these forms, and we train the DeepONet to learn operator mapping from the vx, that is the parameters, to the solution uxt. And the big Vx is sampled from a GRF with RBF kernels with length scale correlation length L chain is 0.5 to test the extrapolation plus. We generate the data set of 100 functions with L test equal to 0.2. And the table, the left table summarizes the L2 relative error of different methods. The pre-trained DeepONet has average L2 relative error of 8.75%, and the physics-informed DeepONet has a slightly larger errors. When we have physics fine-tuned with the chunk net achieves lowest L2 relative errors at about 0.93%. We have when we have new observations, fine-tune with observations always outperforms multi-fidelity method, and fine-tune with observations together works best. The bottom figures is the example illustrating the prediction and the absolute errors of all methods. In the examples, PIN and fine-tune with physics have similar error profiles, and the fine-tune with physics is more accurate than the pins, since the pre-trained DeepONet give better initial parameters of fine-tune with physics. Similar error profiles are also observed between the fine-tune with observation alone and fine-tune with observation together, because their algorithms are similar. Moreover, we consider the different extrapolation levels by using the different correlation lengths for testing. In the right table of the test data set, 100 functions are generated from GRF with L test equal to 0.2, 0.0, 0.15, 0.1, and 0.05. We use 100 data points for fine-tuning method with new observations. decreasing the correlation length represents increasing trend of extrapolations. All the methods outperform the baseline DeepONet and the GPR. And when we have physics, fine-tune with physics outperforms pins in all scenarios. And even under the greater extrapolation with L test equal to L 0.5, it reaches satisfactory errors of about 3%. With 100 new observations, fine-tune with observation together achieves better performance compared with other fine-tune methods with new observations. For multi-fidelity method, the MFN outperforms better as the lower as the level of extrapolation increase, but both are slightly worse than the fine-tune observation method. And last, the figure, the right figure shows the L2 relative error with respect to the learning rate for different approach. The performance of pin is suspect to the change in the learning rate. When the learning rate is low, the L2 relative error of pin is large, and when the pin can while pin can achieve a small L2 relative error when the learning rate is very small, is not very small. The fine-tuning with the branch performs worse than other approach regardless of the learning rates, and the fine-tuning with the entire DeepONet or fine-tuning with the chunknet or fine-tuning with the last chunk layers performs similar and reach a lower error at about 1% at any learning rate between the 10 to -2 to 10 to -4. Next, to evaluate the performance of our method in unstructured domains, we considered the Poisson equations in a triangular domain with a notch. You can see the shape in the heat map. The table summarizes the L2 relative of the methods, and the conclusion are pretty similar with the advection equations result. And the bottom figure is the example of illustrating the prediction and absolute errors of all methods when we have 200 observations. You can see that the GPR and the GPR and MF GPR have similar error patterns, and MF GPR is more accurate than GPR due to the additional lower fidelity data set, and MF multi-fidelity with observation together and multi-fidelity with observation alone outperform other methods, and the MF multi-fidelity observation together is slightly better than multi-fidelity with observation alone. To validate the robustness of the proposed method, we tested the performance on the different level of noise in the observations. We can see in the right figure, with other settings remain unchanged. Increasing noise level lead to a corresponding increase in the L2 relative errors. All methods exhibit better performance than GPR. When the noise level is less than the 5%, the multi-fidelity with observation T reach the best accuracy. As the noise gradually increase to the 10%, the multi-fidelity with GPR method outperforms all other methods. This figure shows that multi-fidelity methods are relatively insensitive to the noise compared to the to fine-tune with observation. Last example is the late-driven cavity flow in complex geometries. And here is the equations where the U is the velocity field and the V is the kinematic velocity, and the P is the pressures. The Reynolds numbers, RE is chosen to be 1000. We consider the different geometry by starting with a square with side length equal to 1 and gradually leaving the left bottom point. With other 3 point fixed. That is the bottom line is described by the Lx equal to minus mx plus m, where m is from 0 to 0.5. The top wall has a unit velocity in x directions. There is a float circulations in the cavities, and the increasing of the value of m represents more extreme cases. We can see the 2 examples in the figures. The top row is m equal to zeros, and the bottom row is the case when m is equal to 0.5. And the goal is to learn the operator mapping from the boundary line Lx to the velocity Ux. We take m equal to 0.02 to 0.4 for generating the training dataset, and select m equal to 0.41 to 0.5 for extrapolation testing. Larger m represents more aggressive extrapolations, and we refer the reference solution is obtained by finite element method with ununiform mesh of 100 times 101 nodes. And for the prediction of the horizontal velocity U, the baseline model GPR has the largest L2 relative errors, and the multi-fidelity methods outperforms slightly outperforms the single fidelity GPR, and the MFN has a better accuracy than MF GPR. You can see it in the figure A, but both are still far from being satisfactory, because their errors are still larger than 10%. But however, the fine-tuning with observation provides a considerable improvement on accuracy, and reach L2 relative error to 10 to -2. And the fine-tune with observation together works the best among all the proposed methods. The prediction of the velocity, the vertical velocity in figure B also has a similar behaviors. And we can see that in the figure, we introduced a slightly new method that is called the adaptive lambda fine-tune with observation T. in the fine-tune with observation T, besides taking the weight lambda as the constant values, we also considered an approach to adaptive update the value of lambda during the training. Specifically, we use the k equal to 0.1 as the initial value, and then after every 100 iterations, lambda update by the gradient descent in these forms. In this way, we increase the weight of the new information and gradually during the trainings, introducing the adaptive adjustment of lambda further slightly improve the accuracy. We show an example for illustrating the prediction and absolute errors of all methods when n equal to 0.5 in figure A and figure B, and most in the examples, most proposed models exhibit better predictions of the velocity field than trained DeepONet and GPR. Among those methods, fine-tune with observations have very accurate predictions of a velocity field in both x and y component. However, the multi-fidelity method has larger errors at the range of the center wax cells and the moving lead at the x directions. This results from the limitation that the finite numbers of data points may perform weakly or even failed in fitting those locations with relative large gradient. And last, for the experiments above, the new observations are randomly sampled in the whole domains, which might not be possible in practice. Hence, we also considered two more realistic cases where 50 data observations are uniformly sampled in certain lines. For the parallel of cases in figure B, the new data points comes from the two horizontal lines, y equal to 0.4 and y equal to 0.6. For the perpendicular case, the new data points come from a horizontal line and a vertical lines, y equal to 0.5 and x equal to 0.5. We use the fine-tune with observation together method for these three cases with 100 new observations. Random sampling in the domain leads to the most accurate predictions, while the other two sampling methods also achieves errors smaller than 5%. Last to conclusion, we provide practical guidelines in choosing a proper extrapolation method depending on the available information and desired accuracy and inference speed in the tables. When we have the physics as information, fine-tuning with physics can achieve very high accuracy, and the computational cost of the fine-tuning depends on the complexity of the PDEs. Sometimes it could be very fast, but if the PDE is very complicated, this could be very slow. And when we have sparse observations, fine-tuning with observation usually have better accuracies than multi-fidelity methods, as fine-tune observation alone only takes a small number of observations. It has faster inference speed than fine-tune with observation together, but fine-tune with observation alone usually has lower accuracy than fine-tune with observation together due to the observation or due to the overfitting. as the multi-fidelity GPR and the multi-fidelity neural network needs to train a new model from scratch. They have a relatively slow inference speed. We can see the conclusion in this figure, in these tables, and the more stars represents better accuracy and faster speed. So that's it. Any questions?
Thank you, Min.
I have a couple of questions. Could you go back to the section where you started the extrapolation results for the advection equation?
Equation. Which equation?
No, the extrapolation results. Almost like the last 7th or the 8th slide from the end.
Extrapolation?
The one before this.
Oh.
Yeah. Move ahead. Next.
So that's the advection one.
The advection equation.
The first
advection,
example
okay.
in your slide.
Okay.
Yeah.
Advection. Okay.
So you mentioned here about the fine tuning with the physics, and you have the results for the branch and trunk, and the trunk last. So how, I wanted to understand what is the difference between branch, trunk separately? How do you incorporate physics in a separate way in the branch and trunk for the new observation?
The branch or chunk or the chunk last, that just means that we change we fix the other part of the network and only change this part of the network parameters.
Okay, yeah, got it. Okay, so you basically you have the new observation and you just train the last layer of the trunk for the last column, and then only the trunk and only the branch and trunk. Okay, yeah. And I had one more question for you. Is like when you talk about extrapolation, when you talk about extrapolation, you mentioned that you have EX plus and EX minus. So L test 0.2 should that not be EX minus? In the same slide, on the same slide.
In the same slide, okay.
Yeah. So here you are testing on 0.2.
0.2, that is the extrapolation is not is smaller than the 0.05 because we trained on the 0.5 and when the L test is smaller, the extrapolation is larger.
So I'm talking about the first, like the table on the left. So you have error extrapolation EX plus. Should it be EX plus or EX minus? Because you are testing on 0.2.
This is EX plus because that is the case that the error increased, and the EX minus is the cases that the error is similar to the interpolations.
Okay, thank you. Very nice presentation. Thank you.
Do we have any other questions, comments for our speaker? Lulu, do you want to add something?
No.
All right. Jordan, do you want to say something?
In the last plot min, when you have the error versus M, you could also compute the error versus the widest distance.
Yes. I think this is not exactly same with the previous examples because this is not from a kernel. I think. Maybe we could use other ways to calculate this.
No, you mean you don't have a distribution. M is you change M.
M is just the slope.
The slope, but you choose the slope linearly, I suppose, right? Not distribution. I see. So maybe you can clarify that the right. So the W2 distance is appropriate measure of complexity when you actually have these distributions. If you don't, then in this case, Lulu, you have to choose another metric of complexity. Here it's very simple. It's just M, but M doesn't mean anything because it doesn't generalize to other. So you may want to rethink about that part a little. Any other questions? There are so many people who are doing DeepONets here, and extrapolation is the holy grail in neural networks. Everybody is happy. They know how to do it.
I had a small question, I guess. Sorry, this is Varun from Brown. So in your advection equation, you're like freezing layers and training probably the last layers with your physics to improve your results. Is that very similar to transfer learning, or how is it different from transfer learning?
Yeah, this is kind of a kind of transfer learning.
Okay. Okay, thanks.
Right. Thank you, Min, for your presentation. Thank you for introducing your recent work to our group and Cron seminar. All right. So this is it for this week's Cron seminar. Everyone has a good Friday and a good weekend. See you next week.